Thank you, sir. The introduction. Thank you, the organizers, for allowing me to give a talk here. So my title of the talk is on the solution of certain Diophantine equation over totally real field. So this is joint work with my supervisor, Dr. Narasimha Kumar. So first I will just recall some known result for Diophantine equation. So first I will discuss some Diophantine equation over integer. So the first famous Fermat-Last theorem is by Andrew Wiles. So he proved in 1994 that the Fermat equation x to the power n plus y to the power n equal to z to the power n. This equation has no solution. No solution means always non-trivial and primitive solution for n greater than or equal to 3. So then in 1997, Darmon and Mirel have studied this equation x to the power n plus y to the power n equal to 2zn. So here they prove that this equation has no non-trivial primitive solution for n greater than or equal to 3. And then Rebate in 1997, he studied about this equation x to the power p plus y to the power p equal to 2 to the power r z to the power p. With 2 is less than or equal to r less than to p. Here p is a rational prime. He proved that this has no solution. And then in 1997, Darmon and Mirel have also studied this equation x to the power n plus y to the power n equal to z square. And they prove that this equation has no solution, no non-trivial primitive solution for n greater than or equal to 4. Then Sixek in 2003, he studied this equation x square equal to y to the power p plus 2 to the power r z to the power p. With r is greater than or equal to 2 and p is greater than or equal to 7. And he proved that there are only finite number of solutions for this equation. And then Ivora in 2003 studied this equation 2x square equal to y to the power p plus 2 to the power z to the power p. But with the condition that p is greater than or equal to 7 and 0 is less than or equal to r, less than or equal to p. And here also the solution are finite number of solutions. So these are the some known result that actually I will use in my talk. So they are basically studied no solutions over integral solution. So now I will just quickly recall some of the known result for Diophantine equation over totally real field. So we start with a totally real field of degree n. Then OK denote the ring of integer and P denote the rational prime. So we first define called as asymptotic solution. So when we study over integral solution, then we are saying that no solution, basically no solution for every, we vary n and we are saying that this equation has no solution. But when we study over totally real field, so this Freitas and Sixek, they first come up with the idea like studying some kind of asymptotic solution. So that so that's why I will first define what do you mean by asymptotic solution. So we say Diophantine equation. I'm taking this generalized generalized Fermat equation, that is AXP plus BYP equal to CZP of exponent P has no asymptotic solution in a set A subset of KQ if there is a constant B KABC depending on KABC, such that if you take the prime P bigger than this constant, then the equation, this generalized equation, Fermat equation, has no asymptotic, no non-trivial primitive solution in S. So basically, here what we are saying, we just take a Diophantine equation. Now we are saying we can find a constant depending on all this color and the total real field K, so that if you take prime bigger than this constant, we are saying that this equation has no non-trivial primitive solution in the set S. So instead of studying all the solution of all these equations, we are finding a constant, and we are saying that if you take prime, if you vary prime bigger than to this constant, this equation has no non-trivial primitive solution. Okay. So in 2015, Freitas and Sixek, so they studied the Fermat equation over totally real field. Basically, they prove that this Fermat equation has no asymptotic solution in KQ. and for a certain class of totally real field. Why I am writing certain class of totally real field? Because this this class depend upon the some solution of SK unit equation. Yeah. So next in 2016, Deconic she extended this result of Freitas and Zizek to the generalized Fermat equation, that is AXP plus BYP equal to CZP, but with the condition that 2 does not divide ABC. Basically, all the ABC are odd. Then in 2020, then Isaac, Kara, and Osman, so they studied this equation x to the power p plus y to the power p equal to z square, and this proved that this equation has no asymptotic solution of certain type in OKQ, like some like certain type, but with the condition that the narrow class number SK plus is equal to 1 and some residual degree f of the residual degree of p over 2 equal to 1 for some prime p belong in OK. So then in 2022, Mukanu proved this result by replacing this assumption, these two assumptions, to 2 does not divide this narrow class number SK plus and 2 is inert in K. So that's why we are interested to study the asymptotic solution of first this equation x to the power p plus y to the power p equal to 2 to the power z to the power p. Basically, you can see with this Deconic result. So she studied for like all these scalar ABC are like odd. So that's why we are kind of study some kind of some solution, some constant where c is equal to here c is equal to 2 to the power r. Basically, this equation does not lie in this Deconic's equation. So now we'll also study this equation x to the power p plus y to the power p equal to z square over k, because here they are assuming this Isaac or Osman, they are just assuming this condition, these two conditions. So we are kind of improve this by like we are kind of we are kind of remove this assumption. Next we'll study this equation bxp plus cyp equal to z square, that is generalized pp2. But here we are taking b is odd integer and c is either odd integer or a power of 2. Basically, we are covering like one is odd case and another is if you take c, one of the constant c is even also. And then we also studied this equation bxp plus cyp equal to 2z square. So here the coefficient is 2 over totally real field k. Okay, so first I will just discuss our results for this equation x to the power p plus y to the power p equal to 2 to the power z to the power p over k. So we consider this equation with prime exponent p and r belongs to n. So k denote a total, k be a totally real field of degree n, and k star is the non-zero element of k, and p, capital P denote the spec of OK. So for any set S inside this capital P, set of all prime ideas, we denote OS be the ring of S integer. So that is all those element alpha belongs to K, so that if you take valuation P of alpha that is greater than equal to 0 for all prime P away from S. And OS star denote the units of OS. Then we denote SK be the set of all primes that lying above 2. And UK denote set of all prime P belongs to SK with that 3 is relatively prime to valuation P of 2. So basically, why these two sets will play an important role in our main results. So now we'll define trivial solution. So trivial solution means we always mean either ABC equal to 0 or ABC is belongs to this set for R equal to 1. These are kind of trivial solutions. So that's why we are kind of remove this trivial solution and study what are the other solutions. So now we define some particular set of solution, that is WK. So this is the set of all non-trivial primitive solution ABC belongs to OKQ to this equation with prime P dividing ABC for EB prime P belongs to SK. So this kind of if you take like 2 divide ABC, sorry, if you take any solution with 2 divide ABC, then automatically, because all this all this prime P belongs to SK that are lying about 2, so P will automatically divide ABC. Now we'll discuss our main result. So we start with a totally real field, and suppose for every solution lambda comma u to the SK unit equation, this lambda plus u equal to 1, where lambda u are SK unit. There is some prime P belongs to SK satisfying this condition, that is maximum of values in P of lambda and values in P of u, is absolute values. This is less than to 4 times values in P of 2. Then this equation has no asymptotic solution in WK. So basically here you can see whatever all the assumptions totally depend on this totally real field K. Where like we are saying that if this SK unit equation has satisfy this condition, that is some prime P belongs to SK satisfy this kind of bound, then this equation has no asymptotic solution in WK. Now so this is basically we are studying asymptotic solution in some some particular set, but now we'll study asymptotic solution in ring of integer. Okay. So we write OES for either degree of K over Q is odd or Eichler-Shimura conjecture holds over K. So that is I'll just recall what is Eichler-Shimura conjecture. So you start with a Hilbert modular form of parallel weight 2 and label n with rational eigenvalue. Then there is an elliptic of over K of conductor n, so that if you take the L function, both EF and AF has same L function. So now we start with a totally real field of totally real field satisfying this condition ES. So yeah, basically here we need this condition ES. So this is also like if you take degree of K over Q is odd, this is also we don't have to take ES. Yeah. So okay, so now here what we are doing, we are also studying SK unit equation. So suppose for every solution lambda comma u to the SK unit equation, so there is a prime P belongs to UK that satisfy this condition. So here you can see in this theorem we take this prime P belongs to SK, but here we need this prime P belongs to UK satisfy this condition same, but along with some extra condition, that is values on P of lambda u, this is congruous to values on P of 2 mod 3. If these two conditions satisfy for prime P belongs to UK, then we say that this equation x to the power P plus y to the power P equal to 2 to the power z to the power P with R equal to 2, 3, this has no asymptotic solution in the ring of integer OKQ. So these are the two main results for this equation x to the power P plus y to the power P equal to 2 to the power z to the power P. So okay, so now I'll just quickly just go through some key steps in the proof of theorem 2.1 and theorem 2.3. So as usual, we just follow this modularity method. So we start with a non-trivial primitive solution of this equation. Then we consider a Frey-Elliptic curve. So this Frey-Elliptic curve is given by this. Now here corresponding to this Frey-Elliptic curve, we have this delta E, C4 and J invariant of E. Then, so the first we prove that there is a constant AKR depending on this totally real field K and R, such that if you take prime bigger than this constant, the Frey curve E over K is modular. And then we prove that if you take prime, if you take any prime Q of a ring of integers, okay. So if you take any prime Q belongs to P away from SK, so that means these are like the prime kind of odd prime, because SK are all those prime lying about 2. So you are saying if you take any prime that is away from SK, the Frey curve E is minimal, semi-stable, and it satisfies this condition that P divide values on Q of delta. So semi-stable means it is either it has either good reduction or multiplicative reduction. And then we prove that we prove that there is a constant Ck depending on this totally real field K, such that if you take prime P bigger than this constant, this residual representation rho bar EP is irreducible. Is irreducible. Okay, so now this is one of the key lemma that will be used in the proof of our main result. So that is, you start with a prime p belongs to sk. So basically here in the previous slide you can see we are studying the solution. We have checked what are the like reduction type of this frailty curve with prime p away from sk. So now here we will study like if you take prime p belongs to sk, then what can you say about the reduction of the frailty curve? So we take prime p belongs to sk. We start with suppose abc belongs to okq is a non-trivial primitive solution to this equation with this exponent p bigger than these two number, maximum of these two number, and you take E with the associated Frey curve. So the first we prove that if you take ABC belongs to WK, then we will have valuation P of JE is less than to 0, and P does not divide valuation P of JE. And equivalently, we have P divide this kernel of rho over EP of IB. This is the inertia group RT. So let R equal to 2, 3. If you take prime P belongs to UK, so basically I just recall that in our like two main result, one is for solution ABC belongs to WK, another is solution ABC belongs to OKQ with condition R equal to 2, 3. So like that's why we are kind of looking what are the like if you take solution belongs to ABC belongs to WK, then what are kind of reduction we have, and if you take ABC belongs to OKQ with this condition R equal to 2, 3, what are the kind of reduction? If you take prime P belongs to UK, then we have these two, either P divide rho bar kernel of rho bar P of IB, I beta, or 3 divide kernel of rho bar EP of I beta. So now I will just go through the proof of this theorem. So we start with a solution ABC belongs to WK of this equation with a exponent P some sufficiently large, and you take E with the associated Frey curve attached to this solution ABC. Then by using two key results of Freitas 6 and 2015, we find there is an elliptic curve E prime over K, so that E prime has good reduction away from SK as a full two torsion, and the residual representation rho bar EP is congruous to rho bar E dash of P. And we have this condition, valuation P of J dash is less than to 0 for prime P belongs to S. So these are the important properties. Basically, this like this property E prime over K has good reduction out from S. This will be very useful. Like this is kind of important condition that we required in the proof. And this obviously this full two torsion also, and this thing also. So how we proceed? Like we just so this elliptic E prime has full two torsion. So then we can express this J invariant J E prime in terms of solution of this SK unit equation along with this condition. So basically we just write the J invariant in terms of solution of this SK unit equation, and now we use this condition. It has good reduction away from SK. And so then we can able to like we just utilize this this thing to get this like to write J prime in terms of solution of SK unit equation, and we just compare with this condition. We just utilize this condition on this lambda comma u to get that valuation P of J prime is greater than or equal to 0 for some prime P belongs to SK. This is how we get a contradiction, because here we prove that it has valuation P of J is less than to 0 for all prime P belongs to SK, but here we got a like for some prime P belongs to SK, we have valuation P of J dash is greater than or equal to 0. And a similar argument also holds like if you take any non-trivial primitive solution ABC belongs to OKQ to this equation with a exponent P large enough and R equal to 2, 3. But in this case, actually, instead of getting this condition that valuation P of J dash is less than to 0 for prime P belongs to SK, here we get either valuation P of J dash is less than to 0 or 3 does not divide valuation P of J dash for prime P belongs to UK. Okay, so these are the like key steps. So now I'll just I'll just go. I'll just recall some local criteria. Like so, here we will provide some local criteria of k for to this equation x to the power p plus y to the power p equal to 2 to the power z to the power. Basically, here we are giving what are the totally real field k, such that this equation has no asymptotic solution, because all our main result is totally depend on this solution of a SK unit equation. But here basically we find what are the explicit field k that are satisfying this SK unit equation, so that we will have this equation has no asymptotic solution in WK. So this is the all this condition for D is congruous to, like if you take any quadratic totally real field, if you take D is congruous to all these things, if you take any D, like D congruous to any one of these condition, then this equation has no asymptotic solution in WK. And then we did for odd degree case. So for odd degree case, we start with here, like you take assume 2 is either inert or totally ramified in K. Then if one of the hypotheses hold, then we this equation has no asymptotic solution in WK. So now I'll just quickly go through this solution of this equation. So we consider this equation, and then we define trivial solution are those solutions with ABC equal to 0. Then we define some like particular solution, that is WK prime with prime P divide AB for every P belongs to SK. So then we define this M-Selmer group of K comma SK. So these are the this is the group of all these elements. Then we define L will be the quadratic extension of K, that is given by K of square root of A, or A belongs to this set. Then we look at this set SL be the set of all prime ideal lying above SK. This is the main result for this equation x to the power p plus y to the power p equal to z square. So we start with a totally real field, and so here what we are doing, we start with you take any element A belongs to this set K of SK comma 2. So and you take L equal to K of square root of A, this quadratic extension. Then suppose for every solution lambda comma u, so like previous case, like this theorem is also depend on this SK unit equation, but as well as SL unit equation. So we start with any solution lambda comma u to this SK unit equation. There is some prime P belongs to SK satisfying this condition, as well as if you take any solution to the SL unit equation, then there is some prime P prime belongs to SL that satisfying this condition. So like if you see the previous result, so previous result we are only looking at the solution of SK unit equation along with this condition, but here we are looking at SL unit equation along with this condition. So we here basically this L are some finite number of quadratic extension. Okay. Then this equation x to the power p plus y to the power p equal to z square has no asymptotic solution in WK. So kind of it's kind of weaker result compared to the previous result, and here is like we have to check also, like for finite many quadratic extension also we have to check SL unit equation. So in order to like overcome this kind of difficulty, so we study this equation like we study in general equation like bxp plus uip equal to z square, and this equation bxp plus 2 to the power y to the power p equal to 2z square. And here we'll discuss the results for these two equations, as well as we'll discuss also how we overcome this kind of difficulties, like we have to this SK unit and SL unit equation, how we will overcome this kind of difficulties also. So we consider this equation. Here we always assume B is odd integer and C is either odd integer or power of 2. Then we define trivial solution are those solutions with ABC equal to 0, and we define some particular type of solution, that is WK. Here WK is the set of all solution with prime P divide BC, or every prime P belongs to SK. Now for any set A subset of P, we so let CL S of K denote this set, and CL S of K of N, this is the n torsion point of this. SK prime, so basically so I just want to say this thing that all our this previous result, like for the two equation we studied, that is totally like we studied for SK, like if you take a solution on SK unit equation and like along with some condition, but here what we are looking, instead of SK here we are looking SK prime. That is the set of all prime P belongs to P with P dividing to BC. So this BC is coming because of this constant B comma C. So now for R belongs to natural number n, let SR be the set consisting of these finite many solutions. So now we'll discuss our main result. So start with a totally real field K along with this condition that 2000 point of CLSK prime of K is 1. That is trivial. Suppose for every solution alpha comma beta comma gamma to this equation. So here basically instead of SK unit equation, here we are saying if you take any solution alpha beta gamma to this equation alpha plus beta equal to gamma square, here alpha beta are SK prime unit and gamma belongs to OSK prime. There is some prime P belongs to SK satisfying this condition. If this condition satisfies, then we say that this equation EXP plus EYP equal to Z square, respectively this equation has no asymptotic. So basically we say this equation has no asymptotic solution in WK and this equation has no asymptotic solution in OKQ. And then the second result that is you start with a totally real field with satisfying this condition ES along with this condition. And suppose for every solution alpha beta gamma to this equation alpha plus beta equal to gamma square, there is prime P belongs to UK satisfying this condition as well as this condition. Then this equation BXP plus 2 to the power y to the power p equal to Z square with R equal to 1, 2, 4, 5 has no asymptotic solution in this set OKQ difference SR. And in particular, we saw that if degree of K over Q is odd, SR is empty. So that means we studied if you take degree of K over Q is odd, then this equation with R equal to 2, 4, 5 has no asymptotic solution in OKQ. So yeah, I'll just quickly go through some of the methodology. Like compared to the previous thing, we just consider for any solution, we just consider the pre-elliptic curve. Then we prove the modularity, and then we prove this irreducibility, and we prove that the pre-elliptic curve has semi-stable reduction prime away from SK prime, and with some divisible condition. Then we for any solution ABC belongs to WK, we get either we get P dividing rho bar P of IP for prime P belongs to SK. And then here also we find another, we get a elliptic E prime. I mean, but here what we get instead of full two-torsion, we get a non-trivial two-torsion and good reduction away from SK prime as well as these two conditions. And then by using a nice technique of Mokano, we relate this J prime in terms of solution of this equation alpha beta gamma with alpha plus beta equal to gamma square. Along with this condition, these two conditions, this condition to get values on P of J prime is greater than to 0 for some prime P belongs to S. So which is a contradiction. This is how we get a contradiction. And a similar idea also work for if you take any solution ABC belongs to OKQ difference SR to this equation with R equal to 1, 2, 4, 5. But here in this case, instead of getting this values on P of J is less than to 0 for prime P belongs to SK, here we get these two conditions, either P divide this or 3 divide this for prime P belongs to U. And similar to this case, the previous x to the power P plus y to the power P equal to 2 to the power Z to the power P case, here also we can also give local criteria for the solution of this two equation. So yeah, these are the references. Thank you. I'll stop here.
Any questions or comments?
Yes, thank you. I wanted to be sure for when you prove the representation is irreducible, do you prove it for every P large enough compared to K, or is there a dependence in
No, it's totally depend on this total real P.
how do you prove it's
Actually, I don't know the technique, but there is a result by Freitas and 6x. So they prove that like you start with a totally real field and you find a constant like depending on K, so that if you take the elliptic curve is semi-stable at prime like at all the prime lying above this rational prime P, then this residual representation is irreducible.
okay? So you look at the equation of the curve and figure out.
Yeah, kind of. take
Okay.
the probability curve and you take the prime like large enough so that this will be this residual representation is irreducible.
Okay, thanks.